Hello and welcome to this video for AQA GCSE Science. Now this video is specifically for the trilogy, the separate science for physics, which you can see at the top left corner of this video says P. So that means it's for physics only, not for the combined science physics students. Okay, and this video is on the solar system. Okay, so let's move on to the question then. It says, explain the life cycle of a star, for example, the sun, and how new elements are formed, and it's worth 6 marks. Now, we know we're going to get some extended questions from 4 to 6 marks on every paper. So we will go through this in a little bit more detail shortly, but we always come back to this after we've done the revision to see if we can now answer an extended question. So let's have a go. So our solar system, this lovely picture in the bottom left-hand corner, okay, it's made up of lots of different things. We have one star, and we know that as the sun. It's quite rare in the UK that we get to see it. However, it is out there, and on the sunny days that we have, we can see it shining bright. We have planets, all right, so you can see them all here. All right, orbiting round, and they orbit a star. Doesn't necessarily need to be our star, which is the sun. It could be any star, okay? So planets orbit a star. There are 8 of them in our solar system. They're large objects in space, and they have to be large enough. This means that their gravity is strong enough to pull in any nearby object from natural satellites. Our solar system is part of a galaxy, and ours is called the Milky Way. I'm sure you're probably thinking, oh, Milky Way is yummy and galaxy, but no, we are thinking science. We're looking at the Milky Way in terms of our galaxy. It is a huge collection of stars held together by gravity, that force. What's a moon then? Well, a moon orbits planets, all right? They are a natural satellite because they're not man-made. Then we've got things called dwarf planets. Now, a dwarf planet in our solar system is Pluto, the one right at the end, okay? It's like a planet in that it orbits stars, but they don't meet all of the rules to be a real planet. Then we've got artificial satellites. They're artificial, so they are human-made, okay? They are man-made. And we have different satellites going around our Earth, our planet, all right, doing lots of jobs. Now, let's look at the order that these planets are in. So we've got our sun here. Then it goes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, okay? There are only 8 of them. So you can come up with any rhyme to remember this. I've just come up with one at random. It is mummies vanished elegantly. Meanwhile, juniors sulked, upset, naughtily. You come up with your own, see if it helps you out. Let's move on to then the life cycle of a star. Okay, so this is quite technical, but once you've done it through a few times and perhaps used a flowchart like this, it may help you. So we start with a nebula. Okay, and that's formed from a cloud of dust and gas. And I've got a bit of a picture here to show you. Now, what happens to create a protostar from this is that the force of gravity pulls the dust and the gas together to form a protostar. What happens is the temperature rises. The star gets denser, okay, as more particles collide together. When the temperature gets high enough, okay, so we're looking at that temperature increase, something called hydrogen nuclei, remember that there, okay, undergoes something called nuclear fusion. And this forms helium nuclei. What this does, it gives that a huge amount of energy, so releases, boom, lots of energy and lots of high pressure, okay? And what that does is it keeps the star, the center of the core of the star really hot, and boom, a star is born, all right? The star then enters a long stable period, okay, and it becomes a main sequence star. Now, this happens when there's an equilibrium or a balance of forces. So when we talked about up here, the gravity pulling lots of particles in, okay, so that's pulling inwards, and boom, that energy of forcing or pushing outwards, okay. When there is actually a balance of these forces, okay, and we've got that stable period, a protostar will become a main sequence star. And this is where our sun currently is. Okay, so that's where we're currently at. What I want you to remember here is we can actually split this in half. We've then got one side if for any stars that are the same size or smaller than the sun, and then over this side for those biggies that are bigger than our sun. So let's go down the left side then. Well, eventually what happens is the hydrogen runs out and the main sequence star starts to swell. As it's swelling, it will either become a red giant or a red supergiant. All right. It becomes really red on its surface, as you can see in the pictures. And what happens is there is fusion of helium and other elements, and new elements are created here. All right. So when it becomes a red giant, that's where those new elements are made. They are created in the core of the star. Now, heavier elements such as iron, or even heavier than iron, okay, are created in the core. The others are obviously created more on the outside. So let's talk about the sun and anything smaller. Once it's become a red giant, it then obviously becomes a little bit unstable. And if it ejects or gets rid of the outside layer of dust and gas, it leaves behind a really, really hot center or a hot core, and we call that a white dwarf. As it cools down though, so as this gets cooler, it emits less energy. All right, and what happens when it no longer emits any energy whatsoever? It is then called a black dwarf. So I want you to imagine, so let's say you've probably watched a fire and it's quite red. As it cools down, it goes more of a white colour. All right, and then once it's totally gone out, it usually turns black. Let's have a look at the other side then. So we've gone through the star swelling up, and it's a massive star. It's bigger than the sun. It becomes a red supergiant. Once this one undergoes more and more fusion, what happens is it expands and it contracts a few times over. And lots of heavy elements are then formed in various nuclear reactions. What happens is eventually it'll go kaboom and it will explode, okay, in a supernova. And those heavy elements are ejected out into space, and they will form new things such as new planets, new stars, okay? Now this will happen ongoing all the time. What happens is that supernova, again, it gets rid of its outside layer of dust and gas, which is what happened over here. And it leaves a really, really, really dense center, okay? And we call that a neutron star. If it is really big, though, it can become a black hole, where this is incredibly dense, but no light can escape from it, hence why it's called a black hole. So let's go on to orbital motion then. Just a quick recap of what we've discussed so far. So things go round the sun and we call that an orbit. Things go round a planet. That's called an orbit as well. Okay, so planets, they orbit a star. So here's Earth going round its orbit, and it's orbiting the star, which for us is the sun. And there's 8 of those, and it's the gravity, okay, that helps to keep that in orbit, but also if they're large enough, they have gravity big enough and strong enough to pull in anything surrounding it. So that has pulled in the moon. So the Earth has a moon that then orbits around itself. So looking at the moon then, yes, we've just said it, it orbits a planet. It's a natural satellite. We didn't make it and put it there. Artificial satellites, though, we have got going around the Earth, but they are man-made. Dwarf planets, that's those tiny ones like Pluto. And remember, this guy is your friend, Mr. Gravity, okay? That is the force that creates orbits. Okay, I'm on to a detailed slide here, and this is for higher tier students. So if that's not you, you can fast forward and catch up with me at a later point in the video. If you are, this is for you, and you'll see in the top left corner, this is all for you. So we've just been talking about gravity being that force that creates these orbits that we've just looked at. An orbit is something, an object traveling in a circle. Okay, it's constantly changing direction. So this Earth is not going off in a straight line and going off in that direction. It might be trying to, but actually it's constantly changing direction. Now, as it's doing that, it needs to constantly accelerate. All right, and therefore it's constantly changing its velocity, but not its speed. Now, if you haven't watched the video, you want to head over to the video that talks about scalar and vector quantities. But it's constantly changing its velocity because it's changing its direction. Imagine going round this roundabout. You have to turn that steering wheel, so you're changing direction all the time. Now, for an object to actually move, there must be a force acting on it. Now, this force is always directed to the centre of a circle. So the cars going around here have always got a force going towards the centre of that roundabout. I want you to come over to this picture down here. So we've got a star in the middle and we've got a planet. This is the same planet, but obviously at different points in its orbit going round. There's a force, it's known as gravity, pulling it towards the centre of the orbital circle at all times. However, and I'll tell you some ways to actually go and try this out. The planet is actually trying to move in the direction of the arrow all the time. Obviously, that is changing. And we need to know that is a right angle to its acceleration. Okay, so let's recap. A force is needed for an object to accelerate. We know that it has to keep accelerating to keep this orbit going. Okay, now that force is pulling towards the centre. The force would cause the object to fall towards whatever it was orbiting. For example, if this planet stopped moving, the force would pull it to the centre. As the object is moving, it's changing direction. But the object keeps accelerating towards what it's orbiting around. And we call this instantaneous velocity. Now, if you get a question on this, what you need to know is that the instantaneous velocity keeps it in a circle. Now, the instantaneous velocity is always at a right angle, okay, to its acceleration. I want you to imagine, I'll do it two ways. Somebody in the middle, holding hands with somebody here. Now, this person in the middle is pulling this person in. Now, if this person is not moving, they are going to be pulled towards the centre. That's what we've said here. Okay? If this person on the outside was to try and walk forwards, and I want you to try this with somebody, try and walk forwards whilst this person is pulling you towards them slightly. Okay, and as you're walking forwards, you will actually be pulled towards the centre, and I guarantee that you will walk round in a circle. You're not actually physically changing the direction yourself, you're just keeping walking forward. But if you were to trace where you've walked, you would walk round in a circle. Another way you could do this is having somebody in the middle, yourself, having a long piece of string with a ball or a conker on the outside. Now, if you make that object go round in a circle, okay, it's got to keep accelerating, but there is a force pulling it towards the centre at all times. If you were to release and let go, so stop that force, so if you were to get rid of this force because you're letting go of that string, you would actually notice that this ball or conker would actually fly out at a right angle. Now, if you've ever watched, I don't know, let's say hammer throw, for example, that's what happens. They swing round and round and round, and once they let go, the hammer throw is released at a right angle to that force, and it travels out to the field. So let's have a look then up here at some more orbital stuff. Now, we've got the sun in the middle, we've got Mercury here, and let's say Venus here. Mercury is going round at 40 kilometers per second, all right? And Venus here is going round at 30 kilometers per second, so actually slower than that, closer. Now, what we need to know is the closer to the star or the planet, the stronger that force is going to be. The stronger the force, the faster this planet or star or object needs to orbit. Imagine going back here, if someone's trying to pull you in harder, You will go towards them unless you actually speed up how fast you are traveling in that circle. Try it. Have a go. Okay. The further away it is, it doesn't need to travel as fast. Okay. So remember that. The smaller the radius, the faster it must orbit. Here. Small radius, but faster the object. Okay. If we've got something called a stable orbit, if the speed or object of the object changes, the size or the radius of the orbit must change as well. So if this planet here decides to go 50, then what does the orbit need to do? It needs to get smaller, and it'd probably end up somewhere like this. I'm just going to quickly show you with this picture down here. So we've got the Sun, we've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The closer it is, the smaller the radius, the faster it's going round. And we can see that here. So it takes Mercury one loop, so one orbit, 88 days. Mars is a lot further away. That's 687 days. Jupiter, oh my goodness, 12 years. So if we class one orbit for Earth as 1 year, in 88 days of 1 year, Mercury would have already been round it. Mars will be halfway round, and Jupiter, it'll have hardly travelled at all. So coming back to the question then. So it says, explain the life cycle of a star, for example, the Sun, and how new elements are formed. Well, it's really important that we kind of find out what the command word is. Then we know how to structure our answer. So here, the command word is explain. You may get some like compare, evaluate, justify, discuss. Okay, so it's really important that you actually learn what that means. So we then look at the topic. Well, we need to know what we need to go into our brain and access our revision about. So this is asking us about the life cycle of a star and the formation of new elements. So that's where we should be going for that information. And we have to focus our question to certain things. So it's given us an example to look at as the Sun, and also the formation of the new elements, not just what are they, it's all about how they're formed. So we can use our ideas framework. That's identify, describe, explain, apply, and be specific. So we would always identify things first. What things do we know? That short answers, maybe key terms, and quick words. Then we describe them. So whatever we've put in our identify, we will describe them. So say what it maybe looks like, what the main characteristics, okay, the main points. Then we go into our explain. So this is where we give detailed sentences and we talk about reasons how or why something happened. Now in this question, it's asking us to explain the life cycle of a star. So we'll explain how and why, and especially when new elements are formed, we'll say how and why they happen. Then we have to link to the topic and the focus using examples. So we have to make sure we link the life cycle of a star to the Sun, and then how new elements are formed. And we have to apply it to those specific examples. Head over to the yellow box then. We can use these connective words and it helps us structure our answer. As a result, we should be able to access higher marks. Therefore, try and use as many of these as possible. And the impact of this is that your marks should be as high as possible. Have a go. Let's have a look then. So we've got a marking band criteria down here. So once you've written your answer, you can actually go through and see where you think you would get to. We would first of all look at our identify and our describe. What's our knowledge? So we say knowledge, application, explanation, or no apply, say why. So we would go through our basic knowledge. What can we identify? Well, we can identify that flow chart that we looked at. So we'd start with a nebula, to a protostar, to a main sequence star, then to a red giant or a super giant. If it's a normal red giant, it'll go white dwarf, black dwarf. If it's a super red giant, it'll go supernova, and then a neutron star or a black hole. And we would just mention what elements were created. Now, we'd say that elements such as iron were created from the core of a star. Then we need to apply it to the Sun. Well, the Sun is not a big size. It's currently stable, and we know it's going to be a main sequence star for billions of years. The Sun is actually a red giant, okay, so creates elements lighter than iron. A super red giant creates elements heavier than iron, including planets and stars. Now, a main sequence star is in a long, stable period because those forces are balanced. And then we need to go into our explanation, say why. Well, a nebula converts into a protostar due to gravity pulling together particles which collide. As temperature rises, hydrogen nuclei undergoes nuclear fusion and turns into helium nuclei and releases lots of outward pressure, that energy, okay? Now, that creates a main sequence star. As hydrogen runs out, the star expands to form a red giant, and there's fusion of helium and other elements. When that becomes unstable, all right, it ejects the outer layer to become a white dwarf, which cools down eventually, and once it emits less energy, it can become a black dwarf. On the alternative, a super red giant, there's more fusion. It expands and contracts several times over, and there's an exploding supernova, which ejects the outer layer of dust and gas into space and leaves a very, very dense core and neutron star. If the neutron star is big enough, it can then become a black hole. Remember, a black hole is so dense that no light can escape from it. Okay, have a go at revising this topic area. Have a go at the question. Now we've looked at how we'd structure it, and then see if you can come back to the marking band and see what you'd give it. Bye for now.